some city and going through all other cities once and only once and returning to the starting city. Formally, finding the shortest Hamilton path in a fully connected graph. Now have a look at the informal way of the traveling salesman problem. A finite sequence of n towns with a certain distance d between every possible pair of towns. We assume you travel between the towns in straight lines or edges. Must travel through every town and return to the town from which we originated. This circuit through all the towns is known as a tour. Must not pass through any town twice except for the starting town, because it is also our ending town. Must find most efficient solution. The sum of all distances traveled must be as small as possible. This solution is known as the optimal tour. This is a simple TSP instance. Here we have some points to connect. We can connect those points in several ways. But the best solution is connecting them in a way we can get the optimal tour, as we mentioned before. We have already discussed the informal aspect of the traveling salesman problem. What is the formal representation of the traveling salesman problem? In the traveling salesman problem, which is closely related to the Hamiltonian cycle problem, a salesman must visit n cities. Modeling the problem as a complete graph with n vertices, we can say that the salesman wishes to make a tour or Hamiltonian cycle, visiting each city exactly once and finishing at the city he starts from. There is a cost Ci, j to travel from city I to city j. In a symmetric TSP, Cij equals Cji. The salesman wishes to make the tour whose cost is minimum, where the total cost is the sum of the individual costs along the edges of the tour. For example, in the figure below, the minimum cost tour is UWVXU with cost 7. The formal language for the corresponding decision problem is given below. How hard is the traveling salesman problem? If we have 4 cities, the number of different routes are equal to factorial 3. That is, we can have 6 different paths. And if the number of cities are 5, we can have 24 different routes, since factorial 4 is equal to 24. In this way, look the number of different routes if we have 17 cities. Now we can identify that when the number of cities become increased, the number of routes can exist will become very large. If n is the number of cities to be visited for the traveling salesman problem, then factorial n minus 1 is the total number of possible routes. Following this basic formulation, an exponential relationship exists between the number of cities and possible routes. For instance, if there are 5 cities, there are 24 possible routes. For 6 cities, 120, and so on. As the amount of input data increases, the problem increases in complexity. Thus, the computational time needed renders this method impractical for all but a smaller number of cities. We have already discussed how hard is the traveling salesman problem. Now we are going to discuss the problem, why is the traveling salesman problem difficult to solve. Finding the best solution may entail an exhaustive search for all combinations of cities. This can be prohibitive as n gets very large. Heuristics like a greedy route doesn't guarantee optimal solutions. The following algorithm shows that a fast heuristic algorithm for the traveling salesman problem. A two-approximation algorithm outputs problem solutions no more than twice the cost of an optimal solution. The two-approximation algorithm for the traveling salesman problem presented by Coleman begins by computing the minimal spanning tree whose weight represents a lower bound on the length of an optimal TSP tour. The minimum spanning tree is used to create a tour whose cost is no more than twice that of the minimum spanning tree's weight, as long as the cost function satisfies the triangle equality. The following algorithm implements this approach, calling Prime's minimum spanning tree algorithm as a subroutine. Following are the steps of the two-approximation algorithm. First, select a vertex R from graph G to be a root vertex. Then compute a minimum spanning tree T for graph G from root R using prime, and let L be the list of vertices visited in a pre-ordered tree walk of T. Return the Hamiltonian cycle H that visits the vertices in the order L. Illustrated above is the operation of approximation traveling salesman problem tour. Part A of the figure shows the given set of vertices, and Part B shows the minimum spanning tree grown from root vertex A using Prime's minimum spanning tree algorithm. Part C shows how the vertices are visited by a preordered walk of T, and Part D displays the corresponding tour, which is the tour written by approximation traveling salesman problem tour. Part E displays an optimal tour, which is about 23% shorter. Up to this point, we have discussed about the simple intermediate algorithms and heuristics. But these are less complicated general algorithms and heuristics used to solve the traveling salesman problem. Also, these algorithms does not guarantee the optimal solution for the problem. So, what is the best solution? Advanced heuristics. These are highly specialized algorithms, many of which, either alone or working in conjunction, are capable of optimally solving symmetric TSP problems. Their specialization limits abstraction to more discrete traveling salesman problem variations and certainly to other types of optimization problems. Meta-heuristics. Meta-heuristics are semi-stochastic approaches to solving a variety of hard optimization